All right. Good morning to all, and welcome to this ISTEC Distinguished Lecture this morning. For those of you who are new to ISTEC, ISTEC is the Information Science and Technology Center here at CSU, covering all aspects of information sciences and technologies. My name is Edwin Chung. I'm a professor in electrical and computer engineering, the director of ISTEC. This is Anura Jayasumana, who is the Associate Director of ISTEC, for those of you who don't know. ISTEC has many activities throughout the academic year, including holding research fora for different areas of interest across campus. We have representation from all colleges across campus, so this is really truly an interdisciplinary, multidisciplinary approach to the information sciences and technologies. Well, one of the events that we have are distinguished lectures. And today we are very privileged to have a very distinguished lecturer to give a talk this morning. And to introduce the distinguished lecturer, I'm going to get Tom Siller up here. Tom is one of our current co-chairs in our Educational Advisory Committee for ISTEC and has been instrumental in many important activities on campus. Tom? Sure. Yes, you do.
Okay. Well, welcome everyone. This is a real special privilege for me because this isn't just a distinguished speaker. This is a good friend, a man who's had a huge influence on my life. This is Dr. Jacobo Bialak, who is a distinguished professor at Carnegie Mellon. He is currently the Hammerschlag University professor. I like the fact, though, that he was the original Paul Christiano chaired professor. Paul Christiano was my advisor. He was my co-advisor, and they embodied, to me, teamwork as faculty, because they truly worked as faculty. Jacobo has a long, distinguished career. I will not talk long because he doesn't want me to, but I will highlight the fact that he is a member of the National Academy of Engineering, corresponding member in Mexico, distinguished member from ASCE, and one short story. We were talking about it earlier because it made a huge difference in my view about research. In 1985, we were sitting at a meeting in Washington, D.C. about earthquake engineering. And Jacobo is from Mexico City. He has family in Mexico City. And in 1985, we're at this meeting, and an announcement came in that an earthquake had occurred in Mexico City. And I suddenly realized I'm sitting next to a person who has his mother living there and all his family, and earthquakes took on a different role for me then. It stopped being just an academic thing. But it is a great pleasure for me to just turn it over to Jacobo because he's a much better speaker and has more to say than I do. So Jacobo, I hope that's enough. Please come up, take over.
Thank you, Tom. Thank you, Professor Lee, and thank you all for being here. I understand that this is the first lecture that you have on civil engineering. So I hope I can give you an overview of one aspect of the work that is done in this area and its relationship to some of the activities of ISTEC, which I think there can be some. And so the title that I have given is End-to-End Earthquake Simulation. This is the application that I use as a vehicle for our work and for my presentation today. Although the work comes, that's really the primary work. But this is an example, and I want to tell you about some of the activities that we have because it involves verification, validation. We look at data, and it involves multi-scale modeling in computational science and engineering because we work actually at different scales. There are two names that I listed here because these are the two people most responsible for obtaining most of the results that I'm going to show you today, in addition to me. Ricardo Taborda is now a faculty member at the University of Memphis. Gitis Viridor works in consulting. So let me tell you in general a little bit about the motivation. This is in geosystem science and also in engineering. And actually it applies to many different areas, but this is the approach that we take. So we actually have a problem in the real world. I start here. There's a pointer that I don't know if you can see. It's a very small dot on the right. So this is the the real world that we want to study, understand, or modify when we're in engineering. And in order to study it, we actually look at data, so it helps us by understanding the phenomenon that we want to examine. We want to build a mathematical model that we can then analyze and then go to several processes. So one is the verification. And in the terminology that I'm going to be using, is that means making sure that our methods for solving our mathematical model are correct. And then we actually perform simulation, trying to simulate real situations. And then we do validation. Here is where we again compare the results of our mathematical model with observations in the real world. And if they agree, then we say, okay, fine, now we understand, we can act on it. Usually they don't agree. And therefore, we need to modify, we need to look at additional data, modify the model, and there is a process of optimization that goes here, or inversion, that I'm not going to talk about, but that's really the one that drives these different cycles, because we actually keep iterating, improving the models, and then looking again at the results and so on. So this is a very general process. I'm going to talk about it in the context of the problem that I just mentioned. And to give you an idea what we mean by end-to-end problem in earthquake engineering, we actually start at the source in some cases, so that there is a fault somewhere that can be near or far from the area, the region of interest. And then there is the propagation path. This is going to create waves. All this involves wave propagation. I won't go into the mathematics of it, but this involves waves in different systems, mainly elastic systems with attenuation. And then it reaches the area of interest that can be an entire city. Like Tom was mentioning Mexico City. This could be Mexico City with all the buildings. And then we're interested in determining several things. Number one is, what is the ground motion to which these structures are going to be subjected? And we also want to know then what is the response that the structures are going to obtain, and then the performance. And also, how do the presence of an entire city affects the ground motion? Because sometimes we measure that, and we want to know whether it has an effect on the free field or not. And that's what you see here at the bottom: source, propagation path, side effects, urban impact. So what I hope to do today is give you a taste of several of these aspects without going too deeply into all of them, but just give you a flavor of the kind of work that we do in this general area. So this is what I'm going to be doing here. Our natural laboratory, most of the work that I'm going to be, in fact, all of the results that I'm going to be showing today are in the LA basin, Los Angeles basin. That's a natural laboratory, and I mentioned this SCEC. This is an agency. It's actually a research center. It's a national research center, Southern California Earthquake Center, that started working very seriously after the '94 earthquake in Northridge, where it was felt that there wasn't really enough information to understand what the ground motion is and why structures behave the way they do. It caused a lot of damage, and here it's mentioned. I won't go through all of them. But this center was created soon before, actually, that earthquake. But I'll just focus on this line that I wrote here. You can read the others. What happens is about 50%, because of the seismic hazard that exists in this area, there are so many faults, and the large population and construction, about 50% of the seismic risk in the country is concentrated in this region. So there is a very, this is a very significant region. I'm sure all of you, if you haven't seen the movie, are familiar with the San Andreas Fault anyway. And not everything in the movie was true, but a few of the things are. Most of it is not. But that's not the only one. This is the major one, but there are some that are actually within the Los Angeles basin that can cause more damage than the San Andreas because they are local. So I'll talk a little bit about that and how we go about modeling in general. So we use this model. Starting in '94, people started developing, because in order to model, as I said at the beginning, we need data. That means records from earthquakes, and we need models. So here we need to to know what the stratigraphy is, and if we're going to develop models of the Earth that we can actually analyze and put into the computer. That effort started in a very serious way right after that earthquake. So this is an effort that has been going on for over 20 years to develop the models. So how do I divide the talk? I'll talk first about ground motion, and then the general methodology, just a few words about it. And then I'll show you some examples of verification and of validation. And then I'll move on to give you also in a very even more encapsulated form how this ground motion affects the city, and sometimes we call it site-city interaction. And a little bit about the methodology, and then some application with some data in between. Okay, so as I mentioned, one needs to know the geology and a material model that this is actually the way this is in Los Angeles. There is a big basin. This is 9 kilometers deep. What has been observed, and this is very general, is that this shows the shaking. And you can see it goes from purple to yellow. This is areas of more shaking. And something that we've known for a very long time is that areas that have, and this shows the type of soil that there is and rock, for softer and harder, that usually in softer soils there is stronger motion, and also it has to do with the depth of the layers. If you have deep layers, they are going to cause larger motion of longer duration, and therefore it's going to represent a higher hazard for the structures. What is important is this is not completely quantified. You know, we know it in global terms, but we don't know sufficiently, and there is a lot of uncertainty on how we incorporate that into design methods when we actually want to build structures. Of course, we know some of it. Everybody has building codes, but they are not as good as we would like them to be. This is the methodology we use that we use in our group. We use a code, as I will show you later with some numbers. We have a lot of elements in the analysis. These are large regions. So we use parallel computers for all our work in this area. And over time, we've developed a code that we call Hercules that is based on the finite element method. It's a finite element tool, and it's octree-based, which means it has little cubes of this shape. And they are of different sizes. They are all cubes because they minimize storage, but they are different sizes because as the waves travel, as they encounter for a given frequency, as they encounter softer materials, the waves are shorter. So we need to have smaller elements in regions where the soil is soft, larger elements where they are large. If you make them all small, then the problem becomes almost unmanageable. So we need to have different sizes to make it efficient. So we have the input data. It's very important to have a model, and that's why the LA region is a very good one. Typically, we talk about the material model. We define the model by its density, the velocity at which the waves propagate. There are two kinds of waves in elasticity. And there is also attenuation parameters that we use. There is internal friction in the material. All this presentation today involves only linear behavior. We have done work with nonlinear, but I've chosen to, in this overview, to talk just about the linear analysis. Then we need to mesh, and refinement has to be done automatically because the property change once we have the model, and this has to be partitioned between the elements. We need to generate the source at some distance, wherever it might be. Then there is the solution stage, and then the output data. This can be either relatively small or huge. If one wants to store the results of an event everywhere in the volume, we can have of the order of, say, 400 terabytes for one event because of the number of elements. I'll give you some dimensions later. We don't do that. We select planes on which we want to store in general, although sometimes we learn a lot from visualizations, and to see how the waves travel internally, it is helpful to do three-dimensional. Well, it's four-dimensional, 3 spatial dimension plus time, but we do it very seldom. So let me talk about verification. and validation. I'll start with verification. And I'll give a physical situation that I was encountered a few years ago. It started in 2008 when California decided for the first time to go through these drills to try to, for emergency management, to pretend that there is an earthquake and then act on it. Other countries, Japan, have done it for a very long time. The US didn't. And they created what is called the shakeout scenario. So this hasn't occurred, and hopefully it won't, but it's plausible. So it's a magnitude 7.8 occurring along an area. This is 600 kilometers by 300 kilometers. You can see how long the fault is. That would give rise to an earthquake of magnitude 7.8. Typically, just to give you an idea, the Northridge was 6.1, and it's logarithmic. So it's almost 100 times stronger. And this is the information that is needed. So one needs the material model, then the definition of the fault, and also how it varies in time. This shows how much it slips along the fault. And for this exercise, because several million people participated, and they actually pretended that the earthquake was occurring, and then this affected reviewing the structures, hospitals working, schools, etc., they wanted to make sure that the records that were being used, we call them accelerogram, were reasonably correct. So there was an effort within this organization, SCEC, of several groups that we work on doing this kind of simulation, trying to do the same simulation together so we would obtain similar results. These problems, of course, there is no exact solution against which we can compare, so the verification is through different simulations. So the kinds of results that we get, this shows, for instance, the distribution of the peak ground velocity in the region. Along the fault is strongest, but then it turns out that the wave travel into the Los Angeles basin. There are areas where it is also large, and this is another basin, Ventura, where they are also large. And this is one piece of information that one can get. We look at different types of information in order to be able to take action. And I want to show you, there is a line here with dots along which we actually look at the records, which seismologists are very careful about this. They call them synthetics because they are not real. And you cannot see all the details. I want you to look just at the general shape. This is coming from the source, and it's near the fault. So you can see that they are fairly, this is in San Bernardino, near the mountains. And this is the point closest to the fault in this diagram. And you can see that the signal looks fairly simple with a very large response. It's a simple pulse. And then as we move in this direction, this shows a cross-section with the material properties. So here it came from the source, and then as it crosses little basins, you see that the motion gets amplified, it gets a little longer, then it gets into a flat region, it becomes small again, then it gets into the LA basin, and it's very large. And these are the kinds of things that we want to learn and quantify so we can use them when we need to do engineering. And here, if you're familiar with the LA region, this tells you various points. So people say, oh, I don't want to live in Monterey Park, and things like that. So we tell them, don't believe this blindly, but it's actually telling us. And another motivation for doing simulation, which I haven't mentioned, is that, of course, there are records from earthquakes, but not sufficient records. The actual data is relatively scanty to be able to take action or to get a full understanding, and that's why the simulations can help augment the information that one has available. So this is that. Then this shows comparisons between the three groups. So this shows the distribution of peak ground velocity similar to what I showed you earlier. This is peak ground displacements. Those are all quantities that are needed to understand how strong the earthquake is. So this is group number 1, that's ours. This is 2, that's one at USC. This is URS. People were working at a company at the time. And this is San Diego State University. We collaborate. So we take exactly the same model, and therefore any differences that we obtain will be in the way that we discretize and in the way that we solve. And it took us months to get to this kind of comparison where it looks alike, or look at this, or getting to this point where there is the three records are on top of each other that you can see here. So let me now show you about validation. Validation is we take a given event, so this one did occur, and we compare against data. So we try to get the best information available. So here we get the source, and this is actually an inversion problem that people try to find from all the records that are obtained throughout the region. One tries to infer what the slip was along the fault. So the slip in centimeters or meters, this is 1.5 meters for this earthquake that I'm talking about. This is a small one. And one also needs to know how it behaved in time. So that we call the source model. Then we have the material model. Then we can do computation, similar to the one before, but in this case, we actually compare against data. So here in the LA region, there are all these records available that for this earthquake. And we took a number of points. We actually used all of them for some parts of the comparisons. And several people have worked on different models for this region. And I'm showing you here 3, and they have also been done in collaboration. People know about what each other is doing, but it actually represents 3 different models. They come from the knowledge of the geology. As you know, there is oil in this area, so there has been a lot of oil exploration. So there is a lot of information from the 40s and earlier that becomes publicly available after 25 years. And people have the travel times, and there are boreholes, and so on. So different people come up with different models. And we wanted to see which of these 3 models is closer to the data for this particular earthquake. So I'm going to show you some results. A little bit of information about the size of the problems that we are doing. The maximum frequency that one wants to simulate dictates in a way the size of the problems. Because, and we want to go to fairly high values. Typically in engineering, we are interested in frequencies up to about 10 hertz. So this is very small to compare to electrical engineering, but we call this high frequency. Small frequencies, 0.25, 0.5. Trying to get to 4 hertz is a big challenge to do it deterministically. So we combine for higher frequency with stochastic methods. But even going to 4, for the 3 models, the first one used about 5 billion elements. The other 2 that were more detailed had about 15 billion elements. Remember the section, I didn't tell you, but in this case it's about 100 kilometers. And in order to capture the waves, the smallest elements are about 5 meters. So you can imagine why we get that many. The computations were done in Blue Waters, which is one of the large computers in the country, using 96,000 processors. And then we took 100,000 steps. That's because of the method that we use. And normally we decimate. So we don't store all of them. They are not all physical. For stability, we need this so many steps. And then the duration of the total computation on this computer with this many elements, for this one it took about 2.5 hours, 7 on this, almost 8 on that. An interesting thing that we are actually quite happy with our code, meshing this number of elements took about 27 minutes, and it's done completely automatically. This is one of the advantages of using blocks. Those of you who work in this area, getting meshes with this number of elements is not easy. Most of the effort goes into getting the mesh. Once you have it, then solving is fairly fast. And I'm going to show you results, observations versus synthetics at a couple of stations. And there are motions in 3 directions, north, south, east, west, and up, down. You don't need to look at the details. I just want to give you a general sense. And here is shown the location. In the lower right part, the epicenter is the star, and the station is located here fairly near. And the red represent data, and the blue simulations. So when we look at this, this is in time, this is taking the transform of this. we are very interested both in the time response and in the frequency response, because structures have properties that are usually measured in frequency. So we want to know what excitation is in frequency. So we typically look at both. And for this record, we say, wow, looks great. Then we look at another one, and that is at some distance. And this one also looks reasonable. This is the duration as a measure of the import of the strong phase of the earthquake. The transforms essentially have the same similar distribution. There are some numbers here that I won't go into detail. You know, when we talk about data, we try to quantify. These are different metrics that we use to see what they are. For instance, the response spectra, and then we look at what I showed: peak ground velocity, peak ground acceleration, peak ground displacement, duration, energy, and so on. And then we take some single number that is an average, weighted average of all these quantities, to give us in a single number to tell us how well the agreement is, the goodness of fit criteria with the record. So we measure the differences and we say, well, this was about 6.7, and the person who developed these particular metrics, also as part of a group, John Anderson, if it is between 6 and 8, we call it good. Above 8 is very good. 4 to 6 is fair. Below 6 is terrible. And so here we are still happy. Then you look at this, and you see huge differences. And this is the way it's all over. So the agreement between the observations and the predictions can be very large. And that's why we need to improve the models. And it's very important to have verification, because now we know that these differences are not because of errors in the calculation. We know that our computer program gives us correct answers to our model. So the problem must be in the model. That means the geology is not well represented, the material properties, and the source is not completely well represented. I don't have time to go into detail on how those are obtained, but they are based on a number of assumptions that when we do the three-dimensional model is better, but the source was obtained for a simpler model. So we need to improve on this. But before I leave this area, I'll skip this one because it's similar to the other one. We actually look at the entire region. So this shows the entire Southern California area, and this shows different frequency ranges. So this is for very low frequencies. This is typically good for very tall buildings. If you have 40-story buildings, they tend to vibrate very slowly, very long periods, so very small frequencies, and they can represent part of the response. So this way, this gives us an idea, and actually these are the three models. So you can see that the first model, which actually has the smallest number of elements, seems to be behaving better than the other two. So more detail does not necessarily represent better description of the phenomenon. And this actually shows the distribution. So we have between 7, 8, 9. So at low frequencies, the prediction is quite good. This is not prediction, it's post-prediction. We're taking the record. And this shows the epicentral distance, this very top one, because this is always important. And this is also one of the difficulties. There are very few records near the epicenters. And that's where a lot of damage occurs. And that's where simulations can contribute a lot. So in this case, you can see that it's actually fairly good at all distances for this frequency. A little better near than far, but it's good almost everywhere. As we go to higher frequencies, we begin to see more red. That means the low values, 4, 5. So that means we missed them. So when I showed you the individual records, I picked some that were in the yellow area, and then the last one I showed you was from the red area that is not so good. And then this one is still given reasonable answers, but when we go to the high frequency, then it's getting, this is the final score, and this combines all the metrics and all the frequency bands. You can see that our capability for validation and simulation, well, for simulation, we can do it, but we are not yet close to the answers that we want to see. Our models are not close enough. And how do we improve them? So one way to improve, and it's been going on, it's a continuous effort, is by looking at the inverse problem. That's where those ellipses come in, where I showed you. Because we now have a model that was quite reasonable up to certain frequencies, but it's not satisfactory. So we can actually use the data, and this is an optimization problem, and try to minimize the error between the data that we have, and we have a number of stations, and the results that come from the simulation, and then minimize that subject to the partial differential equations that govern the phenomenon. So this is a problem of partial differential equation constrained optimization. And a number of people work on that. We do a little bit of work on that as well, and I'm not going to talk about it in this presentation, but it's a crucial part of the phenomenon, because this is how we advance from one model to the next model. Then we go through the same cycle again. We see whether we're getting close. There is also a lot of work. This is very computationally demanding and mathematically difficult. A lot of people who've done a lot of work in this area develop a sixth sense where they can do by intuition. Because by looking at where there are discrepancies in the data and the synthetics, they can say, oh, if I put my source, if I change it a little bit, or this material was, we can see the speed of the wave. So we were too slow, too fast. We can change them and adjust them. And before optimization was in full force, that's how the models were being changed. And even today, our capability of handling problems this size is not great. So the mathematical optimization is used, but it's only used at very low frequencies. It does not go to very high frequencies yet. Okay, the second part of my talk is now we have this ground motion. What do we do with it? Well, what we would like to do is then use it as input for our city and then shake the buildings from the excitation that we obtain, because now we have the distribution everywhere. We know where there is strong ground motion or not. So I'm going to, again, just give you an idea of the kind of work that we do. Our code cannot handle real structures because we use finite elements that are very simple. So we need to combine with other codes if we want to have realistic models of the buildings, which people are doing. So we do the ground motion from our code, and then we try to put in that ground motion into a smaller domain that's going to do the analysis of the smaller region. This may be of the order of a kilometer. If we are downtown LA versus 60 or 80 that I showed you for the development of the earthquake. So in this case, we try to do what would happen in a section of Los Angeles, and there is a little, I'll show you by hand because it doesn't show well. It's in this area where we're interested in knowing what happens in buildings there. That was the Northridge earthquake. This represents the trace of the projection of the fault on the surface. So this was the size of it. And this is the strike. That's where the direction. And this shows how the fault was with its displacement distribution along the fault. So we use this as input. And then, of course, the first thing that we try to do is calculate here it is much clearer. So here you see this is an area of interest. And then within that area is this one. We want to locate buildings in different regions. The lighter the color, the softer the soil. And so we put them here, and I'm going to refer to it in a few minutes. So let me mention, within this square, notice that there is a yellow color, which means the softest material, and this material was stiffer. And when I show you how the ground motion is, we'll see that there is a difference in these points versus those points. So the model is capable of actually saying, this material is softer, I respond in a certain way versus another one. So We do this using a methodology that we have developed originally, where we take the entire domain and we calculate the ground motion, but then we take a little box inside and we put in the ground motion to excite a smaller domain. That actually requires some thought because you cannot just shake the base, because otherwise you are creating artificial reflections. So it has to be a seismic motion that comes in, and that has to be done carefully, which we try to do. And then we can look at, first is the free field motion. These are different snapshots at different times, how the earthquake is developing. You can see it started near the source, and then it starts moving out. And this is a zoom within this area. So these are the seismic waves moving along the domain of interest, and now they leave. And here is the scale. And now we look at a line. I'm going to show you the records. Within that square, a diagonal line that goes from this point up here to this point down there. And this is the wave traveling just in one direction. You can see that it's not exactly the same. Even though this is a small region, it actually varies somewhat. It is strongest here, and it is a little weaker here. And then we calculate the spectra of all these records and put them on top of each other. And this shows the range, and this shows the mean value across. And this is very important when we are designing, because you can see that for this earthquake, if your structure has a frequency that is in this range, it's going to be subject to greater motion than if it is in this area. And this is what engineers, this is the kind of information that is used in order to be able to tell how the structure needs to be designed. I want to very quickly show you a comparison with some records. You know, qualitative, it's not the same earthquake, but just to see how the spectra look. This is perhaps one of the most famous from the earthquake engineering point of view buildings in the LA area. It's the Hollywood Storage Building that has been instrumented for many years. And it has an instrument on the roof, basement, and outside in the parking lot. So one can see the difference in the response between the different. It looks more or less like this, and this shows the plan view. So there are records at the roof level, at the basement level, and in the free field in a parking lot. And a large number of records have been obtained in this building for a very long time. And this shows the corresponding diagram that I showed you earlier from our computation. If you remember, for a particular earthquake in 52, this goes by the name of Taft earthquake or Kern County earthquake. And if you see that the overall, it's a very different earthquake, but in the same general region of LA, it has approximately the same shape. So we were actually quite happy to see that. And the reason you see here two lines is one corresponds to the records that were obtained in the basement. Those are the solid ones, and the ones in the free field. The building tends to filter the ground motion. It's a very stiff slab. Of course, it's the complete building on top. So as the short wave wavelengths come, they get filtered. They cannot travel freely because it's no longer a free surface, and there is a reduction. And this actually can have consequences, in this case beneficial in some cases, for looking at earthquakes, because that means that the effective excitation can be somewhat smaller, and that can be taken into consideration. So then we wanted to see what happens when you put a whole cluster of buildings together, and we've done things with different ones. This is just a simple representation, and we select them so that their frequencies of vibration will be similar to those of a real building. And we have 3-story, 13-story, and 40-story models. I'll just show you a couple of results. This is the methodology that we do. So this is the domain reduction method. That here is the source, and then we want to analyze what's happening here, but we don't do it in one step. We divide it into 2 steps. So first, there are no buildings or even the basin, and then we record the motion in some surfaces, and then we use these for the excitation in a much smaller domain of the area of interest. And that allows us to reduce significantly the computational domain. And in fact, let me show you some numbers here. This is step number 1, where we had the complete domain. This was 82 kilometers by 82 by 41 deep. This has about 2.5 billion. Here we can go to a fairly high frequency because it's a small domain, also 5 hertz. It took about 15 hours, one simulation. That gives us the excitation for that earthquake. And then in step 2, which is a much smaller domain, 5 kilometers, the size of which is only 11 million, we use far fewer number of cores, and we can do 30 computations using 23,000 units, when here it took us 270,000 units to do one. And similar, I won't talk about the difference. We actually had 2 types of soil, and those 2 are similar. And here I'll just show you very briefly. This is a fairly busy slide, but I just want you to look. This is the effect of the building clusters on the ground motion. And this shows the peak values, and this shows the percentage reduction. And as I told you, as the waves travel, then the buildings are going to filter some of that motion, and we get about 20%, 10 to 20% reduction over the entire region. But here we got 40% reduction. And this is the one that corresponded to the very soft soil. So the waves actually see it in the model, and this can be of interest. Of course, we also want to know what the effect of this is on the buildings. So we call transfer function. We want to know, the language is similar to mechanical engineering and electrical engineering. We want to know the ratio of the motion, say, that we had under the basement, at the basement level, under the building, compared to the motion in the free field. Because that tells us how the effect of the building is on the ground motion. And the red line is the mean value. The others represent a whole range. So this is a short building, and you see that there is a dip that occurs near the natural frequency of the building. For the taller building, this represents the taller building. We see several dips, then it stays low, dips again, and it stays low. So for the higher frequencies, there is a greater absorption, or let's say dispersion, scattering effects, and it causes a filtering of the response. And this actually represents records, except for this solid line, which is another mathematical simple model from years ago. And if you follow this, this is under 4 different earthquakes. Still, this is real, taken from the Hollywood storage building. And you can see that at first it's about 1. For very low frequency, the transfer function is 1. But then it starts going down in average. And something that has been observed and it hasn't been noticed, or it hasn't been stressed very much in practice, is that there can be fairly large amplifications here at higher frequencies. And we observed them, and we thought that maybe it was the sensitivity of our calculations. But when we saw these records, we say they are there. So we need to understand them better and then learn how to use them when we're designing structures. And this shows the corresponding effect at the roof of the structure. So this is the short building, only has 1 peak, 1 dominant frequency. This is the tall building, so we have several natural frequencies at the building. The black one, you see a black line there, that's all I want to point out. This is the one when there is no interaction. We just take the motion that if we had an accelerometer that was obtained in the free field, and we shake the building with that, then that would be the record. So here, there was fairly similar, but as we go into higher frequencies, they actually become quite dispersed. And we observe this also kind of, the average is taken there, but if we look at the range of it, it's huge, depending on the location and on we had different arrangements of buildings and so on. That's why we had 30 runs. So one can draw some statistics from these results. And then the corresponding figure that was obtained from the roof of the building is this. So again, you see peaks corresponding to natural frequencies of the structure that have been moved a little bit. This was rigid base because the soil provides additional flexibility, so there is more compliance, and therefore the frequency gets reduced a little bit. But here we also see these very, these large responses that were unexpected. And this is taken from a report by Trifunats, but it hasn't been elaborated. So this is something that we're trying to understand and study better. So this gives you a general picture of the kinds of activities that we do in performing this. Each of these requires a lot of attention. If you want to use it for design, we need to look at it a lot more. If you want to understand the ground motion also. And just to conclude, I want to show you two animations where we actually put structures that are not all identical. In fact, if you are familiar with the LA area, the geometry of this was taken from an aerial view, and we just put buildings that would have similar shape and similar by counting the number of stories. As engineers, we like to do all kinds of simplifications. So we say that the fundamental period of a structure is 0.1 times the number of stories. So if you want to have an idea of how a structure vibrates, it's very inaccurate, but it's one that I don't forget. We use other formulas that are better than this when we actually do computations, when we want to guess that. They look at the shape and the size and so on, but that's pretty good. So as an order of magnitude, the ballpark. So based on those things, we design these structures, and I'm going to show you two animations. The first one is just ground motion. So the waves are going to be arriving, I believe, from this side, and the reason that they are two is this one, both of them have the same plan view. The presence, this is the footprint of the structures, but the one on the left doesn't have any structures in it. It's just there to show you the position of the structures. The one on the right, the structures are really there when the earthquake is coming. So you will see, and please, it's not easy to follow the two of them, but the one on the left will be more regular, and we'll see that the one on the right, eventually the waves start going around the buildings and they start modifying the ground motion a little bit. So let me see if I can get this to, we tried it earlier and it worked, so let's see. It's moving. So it starts, this shows the color. This is small amplitude and this is large amplitude. And you see all kinds of waves. The ones that arrive first are called P waves, and then the S waves arrive, and then surface waves arrive. And you begin to see how that one goes more smoothly, and it has the modes corresponding just to the soil, whereas these ones have the presence of the structure. Okay, that's number one. Let's go to number two. So, pardon?
What was the time scale?
It's very good that you mentioned seconds. Yeah, I'm trying to keep sight of the time, but let me see if I can go back. And you can see the scale here. Let's see. The whole thing takes about 20 seconds. I'll tell you. It's 8 seconds now. 12. So it's about 25 seconds, the total duration of the strong part. So everything occurs, I'm glad for the question, because everything occurs in less than a minute. Typically, in California, that's the case. The strong part of the earthquake can be 30 seconds at most, 20 seconds or less. So let's go to the next. And here we will see the waves coming through the ground. See, I knew we were going to be in Colorado, but no. Actually, this animation was performed by computer graphics people in UC Davis. Professor Ma, you may know. his name. So we collaborated on one project, and they designed it like that. So the wave will come, and it goes very fast. That's the P wave, then the S waves, and you'll see how the buildings oscillate. Look at the front. And even the taller ones. This is something very important that I'll mention after you watch. Okay, that's the, so I can say, see, the tall buildings, people usually feel that, you know, they respond mainly in the first mode. You know, that's everything vibrating in the same direction with a very long period. But if you see the pictures here, and we see it from the results, is that they actually, if they are very tall, and if the excitation is in higher frequencies, they will be responding in higher modes. And that can be significant. So the idea that we can actually model tall buildings if we only have earthquakes up to 0.5 hertz, is not quite true. You know, we really need to include higher frequencies to fully represent the response even of taller buildings. And this one is just for illustrations. Earthquake engineers, civil engineers know these facts well, but this illustrates it in a nice way. Okay, so this brings me then to the concluding remarks. So what I've tried to show you is that simulations can help provide detailed description of different phenomena that we want to study. In our case, of the ground motion and structural response, and they serve to augment the information where data are lacking. And we do all kinds of tests in this center because these simulations are now being used for design, and they are being, not just what I showed you today, but simulations in general in earthquake engineering, and they are being used to modify the provisions of building codes where there is not enough data. So there are a lot of tests that engineers like to do before they accept results of simulation. This is a 20-year effort that it has taken us to convince practitioners that this information can be useful. And now they are beginning to accept it. And of course, there is a need to process large amount of data, so and to have good methods to how, when you generate so much, it's very easy to generate from sensors. I also work with those things. We can generate a lot of information, and from simulations we can generate a lot. The important thing is how do we extract useful information? And that, of course, I know is an important part of the ISTEC, and we are struggling with the same thing. So our conclusions on verification, I think we're in very good shape there, because we have, right now, the models that I showed you were from a few years ago, it was up to 1 hertz. As we speak, we're working on simulations up to 5 hertz, and finally, after a lot of work, we're getting the same kind of agreement at higher frequencies, because it's not trivial. You know, you say, oh, just put more elements. All kinds of things happen. Even the models are not the same, because the kind of attenuation varies with frequency. So as we go to higher frequencies, we need to change our models, even under small deformation. But these are reliable. Validation, I put it, quote unquote, reasonable fit. But there is a lot for improvement. It's not ready, so we are not ready yet to say, you know, you tell me what earthquake and I can tell you exactly what the distribution was. So there is need to improve the velocity model, the source models. But as I said, the simulations can help guide the inversion process. And then on the site-city effects, there is influence between the structures. An individual structure may not have such a large effect, but a collection of buildings may be affecting each other and what happens to the ground motion. And there can either be increase in the response, or usually we think of this as a reduction, but it's not always true, so we need to be mindful of that. And with that, that's the end, and I thank you. Please speak up because I can't.
Thank you for the great presentation. I have a question. You showed some elevation
go back to the models and check the physics in the model. How do you determine that whether the issue is the physics of the model or with data collection and then instrumentation that was used to collect the data? Could it be the data is off to some extent?
That could be. But there are so many instruments. You know, one instrument may be off, but you actually look at the overall behavior. So that's a very important question, you know. I showed you for illustration one record, but your question prompts another thought that we have and that we have to deal with. Is that really the best way to tell? Because if you just move some distance away, then it may not be, or maybe the properties here were slightly different. So the comparison has to be done in a more statistical way. So we don't just, I showed you the individual records because it's interesting and we want to see them, but it's not sufficient to tell whether it's right or wrong. In optimization, we actually do take a very large collection of records, and sometimes you do have some that, you know, were outliers and you determine that they were incorrect, so you eliminate them. But typically, when it's done as a mathematical process, the optimization process automatically makes these adjustments to try to adjust the source and the model. Usually when this inversion is conducted, one looks at simple earthquakes, where you think that you know the source quite well, the way that we usually know, and the model is not well known. So we try to improve on the model, knowing that the uncertainty in the source is minimal. But you're absolutely right. But definitely it's not the way, you know, we always report them, but that's why I showed you also distribution, because it has to be done in a statistical sense.
Yes, my question is about the instrumentation process. So how has the instrumentation changed over the last 10, 15 years? Because now, you know, you can measure in remote places and stuff.
That's right.
So I was wondering whether GPS and internet-based technologies are used more widely for measuring these types of things.
They're beginning to be used. And I'm not the best person to answer that, because I work mainly on the simulation aspect, although Interact. I did say that we use sensors in a completely different project at the local level, you know, on structural health monitoring that I work in lab, and we have a rail system in Allegheny County. But it has improved. It has. Initially, I can tell you, all the instruments, typically they are accelerometers, and the ones that I'm mentioning here. And all those used to be analogs. Now they are, of course, all digital. And people use inclinometers. And in buildings, they are beginning to use, well, even drones, with taking pictures and looking at different types. And they use X-rays. So there is room for more. But it has evolved. It's not used as much in the work that I mentioned here. That's used more when people want to determine the structural behavior. So they want to focus on particular areas, then they locate. Here I told you there is one in the roof. Many buildings are instrumented, and they may have hundreds of sensors within a building. And I think, I think we actually have an expert here. You could answer much better this question than I can. But yes, people are, but for the in seismology, most of it is accelerometers that are very sensitive. You know, they are better today, and that's why, you know, the range is better and the possibility of error has decreased tremendously. I know that we're getting late, but I can tell you, we used to correct these accelerometers because they don't get triggered right away. And therefore, one needs to find, because if you just integrate, you would find that you had a final velocity that was not zero, and a huge displacement from the acceleration. And all that has been improved.
So
and
in simulation, do you also take those as boundary conditions to try to monitor something?
we use them when we do inversion. Otherwise, we just compare. So it's completely independent of the simulation process.
Well, you know, we've come to, I Andrew, but before we let you go, we wanted to just finish with presenting our distinguished lecturer with a token of our appreciation. I'm just going to read from this, presented to Jacobo Bialak. In appreciation for your Information Science and Technology Center, ISTEC Distinguished Lecturer, Colorado State University, April 17, 2017.
Thank you so much.
Thank you so much. Thank you all for coming, and
Thank you.
perhaps you could continue asking questions if indeed Professor Bialak is available.
Certainly.